There is light around you almost constantly. It pours from the sun, glows from a screen, bounces from walls, and travels across billions of kilometers of empty space before reaching our eyes. And yet, when we ask the simplest possible question, what is light actually made of, the answer becomes surprisingly strange. Welcome to the Snoozy Scientist. I'm very glad you've joined me tonight. Before we settle in, tell me where in the world you're listening from. Maybe you're already tucked into bed, stretched out on the sofa, travelling somewhere late at night, or simply sitting in a quiet room while everything outside begins to slow down. Wherever you happen to be, make yourself comfortable and allow the day to fade into the background for a little while. And if these slow, sleepy journeys through science are your kind of thing, you can help the channel enormously by leaving a like and subscribing. If you've already done that, thank you for being here and for helping this little corner of science continue to grow. Tonight, we are following something that seems almost impossibly familiar. Light for centuries, physicists argued over whether light was a wave or a stream of particles. Then quantum physics arrived and somehow made the answer both clearer and stranger. A beam of light can spread and interfere like a wave, yet it can also deliver its energy in individual packets called photons. And even that is not quite the deepest answer. Because a photon is not simply a microscopic glowing ball flying through empty space. In modern quantum physics, light belongs to something far more fundamental, the electromagnetic quantum field. So tonight, as gently as possible, we are going to find out what that actually means. What is light made of according to quantum physics? Light is so ordinary that it rarely feels mysterious. It arrives through a bedroom window in the morning, glows from a lamp after sunset, flickers in a candle flame, spills from a phone or television screen, and crosses enormous distances from stars before finally reaching our eyes. We use it constantly, depend on it completely, and usually give very little thought to what it actually is. But the moment we ask what light is made of, the question becomes much stranger. At first it sounds as though the answer should be simple. A table is made of atoms, water is made of molecules, a proton is made from quarks and gluons, so perhaps light should also be made from some collection of smaller ingredients. Modern physics does not describe it that way. The first important distinction is between asking what light does and asking what light is. We know a great deal about what light does. It carries energy. It carries momentum. It can reflect from surfaces, bend when it enters glass or water, spread through diffraction, interfere with itself, heat matter, trigger chemical reactions, and transfer energy to electrons. Those behaviours are measurable. They can be predicted with extraordinary accuracy. But none of them, by themselves, tell us what light is made from. In quantum physics, light is described in terms of the electromagnetic field. This field is not merely a convenient picture drawn over empty space. It is part of the physical framework used to describe electromagnetism throughout the universe. When the electromagnetic field is treated quantum mechanically, it does not exchange energy in an entirely continuous way. Instead, its excitations come in discrete quantum units. Those units are called photons. This is where the familiar phrase that light is made of photons comes from. It is useful, and in many situations it is perfectly reasonable, but it can also create the wrong mental image if we take it too literally. A photon is not thought to be a tiny glowing marble with a surface, an interior, and smaller pieces rattling around inside it. According to the standard model of particle physics, the photon is an elementary particle. The word elementary has a very specific meaning here. It means that experiments have not revealed any smaller constituents making up the photon. By contrast, a proton is a composite particle. It contains quarks and gluons and has a rich internal structure. The photon, as far as present evidence shows, does not. So if we ask what is inside a photon, the best current answer is not another list of particles. There is no experimentally established inner machinery. Yet even calling the photon a particle can be misleading if we quietly imagine the word particle to mean a microscopic grain of matter. Quantum physics changes that picture rather dramatically. In classical physics, a particle is often imagined as a small object with a definite position and trajectory. It moves from one place to another, rather like a miniature pebble following a path. Photons do not fit comfortably into that picture. Light can produce effects that look strongly particle-like. A detector can register an individual photon as a single localized event. Energy can be transferred in discrete amounts. Momentum can be exchanged in a way that resembles a collision, and yet light also produces interference and diffraction, behaviours that are characteristic of waves. A beam passing through two narrow openings can create a pattern of bright and dark regions that is naturally explained through wave interference. More strangely, even when photons are sent through an experiment one at a time, individual detection events can gradually build into an interference pattern, so light refuses to behave like an ordinary classical particle. But it also refuses to behave like an ordinary classical wave. A classical wave is usually imagined as a continuous disturbance in something. Water waves involve water. Sound waves involve oscillations in air or another material. Light does not require a material medium in that sense. The electromagnetic field can exist and propagate through vacuum, and once that field is quantized, its behaviour includes discrete excitations that we call photons. So the apparent choice between wave and particle is too restrictive. The quantum description is deeper than either classical picture. A photon is a quantum excitation of the electromagnetic field. That phrase sounds abstract at first, but it is the central idea. The electromagnetic field has possible quantum states. A state containing one suitable quantum of excitation can be described as a one-photon state. A state containing more excitations may involve many photons. Other quantum states of the same field can behave in ways that resemble the smooth electromagnetic waves familiar from classical physics. So photons and fields are not rival explanations competing to tell us what light is. They are connected parts of the same quantum description. The field is fundamental to the theory, while photons are the discrete excitations associated with that field. And even this does not quite end the question. Because once we say that light is an excitation of a quantum field, another question immediately appears. What is the quantum field itself? Is it the deepest layer of reality, or is it only the most successful description we currently possess? Physics does not yet have a confirmed answer to that deeper question. What we do know is that light is not adequately described as a stream of tiny glowing objects moving through empty space, nor is it simply a smooth classical wave. It is a quantum phenomenon associated with the electromagnetic field, and the photon is the elementary quantum excitation through which that field can exchange energy and momentum. Something as familiar as a beam of sunlight is therefore already telling us something remarkable. The ordinary world is built from descriptions that become far less ordinary when we look closely enough. Long before quantum physics entered the story, light was already causing arguments. The question was simple enough. Was light made from tiny particles moving through space, or was it some kind of wave? For centuries, physicists moved back and forth between those two pictures, often with great confidence, and occasionally with the sort of disagreement that makes modern scientific debates look almost polite. Isaac Newton strongly favoured the particle idea, he proposed what became known as the corpuscular theory of light. In this picture, light consisted of tiny particles, or corpuscles, emitted by luminous objects and travelling through space in straight lines. The idea seemed reasonable for several reasons. Light often appears to travel in straight paths. It casts sharp shadows. It can reflect from a surface as though tiny objects are bouncing away from it. Newton also tried to use his corpuscular model to explain refraction, the bending of light when it passes from one material into another. But Newton's particles were not photons in the modern quantum sense. They were imagined much more like ordinary microscopic objects. The quantum idea of a particle did not yet exist, nor did the electromagnetic field, quantum states or wave functions. Newton's model belonged entirely to classical physics. At roughly the same time, Christian Huygens developed a very different explanation. Huygens argued that light behaved as a wave. His wave theory treated every point on a wavefront as a source of new secondary wavelets. Together, these wavelets could explain how light moved forward and how it changed direction at boundaries. This became known as Huygens' principle. The wave picture handled reflection naturally, and it offered an elegant account of refraction. Instead of imagining tiny particles being pulled or pushed at the surface between two materials, light could be understood as a wave whose propagation changed as it entered a different medium. For a time, Newton's enormous scientific reputation helped the particle picture dominate in Britain. But the wave theory gradually acquired something much harder to argue with. Experiments. One of the most important came from Thomas Young in the early 19th century. Young allowed light to pass through two narrow openings and observed the pattern formed beyond them. If light consisted only of independent classical particles travelling through one opening or the other, it would be natural to expect two bright regions corresponding to the two slits. Instead, a sequence of bright and dark bands appeared. This was an interference pattern. Waves can produce exactly this behaviour. Where two wave crests meet, they can reinforce one another, producing greater intensity. Where a crest meets a trough, the waves can partially or completely cancel. The result is a regular pattern of bright and dark regions. Thomas Young's double-slit experiment, therefore, gave powerful evidence that light possessed wave behaviour. And this particular experiment would eventually become even more important than Young could possibly have imagined, because interference would later sit at the heart of quantum physics itself. The wave description was strengthened further by Augustin Jean Fresnel. Fresnel developed a much more complete mathematical treatment of light as a wave. His work explained diffraction, the tendency of waves to spread around obstacles and through narrow openings, as well as more detailed patterns of interference. By the middle of the 19th century, the wave nature of light looked increasingly secure, but one question remained. What exactly was waving? For sound, the answer was straightforward. Sound travels through matter as organised vibrations of atoms and molecules. Water waves involve water. Light seemed to travel even through regions where no obvious material substance existed. The next major change came with the growing concept of fields. Michael Faraday was central to this shift. Faraday developed the idea that electric and magnetic influences were not simply mysterious forces acting instantly across empty space. Instead, he pictured physical fields extending through the regions around charges and magnets. This was a profound conceptual step. Space could contain a physical condition. An electric charge could alter the electric field around it. A magnet could alter the magnetic field. Another object placed within that field would then respond to the local field at its own position. James Clerk Maxwell transformed these ideas into a mathematical theory. He showed that electricity and magnetism were not separate phenomena, but deeply connected aspects of one electromagnetic system. More remarkably, his equations predicted that changing electric fields could generate magnetic fields, and changing magnetic fields could generate electric fields. These disturbances could sustain one another and travel through space as waves. When Maxwell calculated their propagation speed, the value matched the known speed of light. That was not a small coincidence. It suggested something extraordinary. Light itself was an electromagnetic wave. Visible light was therefore not a special substance produced only by things that glow. It was one part of a much broader family of electromagnetic radiation. Different electromagnetic waves could have different wavelengths and frequencies while belonging to the same underlying phenomenon. What human eyes detect as visible light occupies only a narrow region of that spectrum. At lower frequencies lie forms such as infrared radiation, microwaves and radio waves. At higher frequencies lie ultraviolet radiation, X-rays and gamma rays. The universe, it turned out, was full of forms of light that human vision simply cannot see. James Clerk Maxwell's theory was elegant, but physics becomes much more convincing when nature agrees in the laboratory. That confirmation came through Heinrich Rudolf Hertz. In the late 19th century, Hertz experimentally generated electromagnetic waves using electrical equipment and detected them some distance away. He showed that these waves could reflect, refract, interfere, and behave in the ways Maxwell's theory predicted. They travelled through space with the expected electromagnetic character. The classical picture of light had reached an extraordinary level of success. Light was an electromagnetic wave. Electric and magnetic fields oscillated together while the disturbance moved through space. Reflection, refraction, interference, and diffraction could all be understood within this framework. For a moment, it must have seemed that the ancient argument had finally been settled. Newton's classical particles had lost, Huygens' waves had won. But nature had kept one complication quietly in reserve. Because although classical wave theory could explain an enormous amount about how light behaved, it could not explain everything. And when physicists eventually looked closely enough at the way light exchanged energy with matter, the old particle idea returned. Only this time, it returned in a form that neither Isaac Newton nor Christian Huygens could have recognized. By the end of the 19th century, the wave theory of light had become remarkably successful. James Clerk Maxwell's equations explained light as an electromagnetic wave, and experiments had confirmed that electromagnetic radiation behaved exactly as the theory predicted. Reflection, refraction, diffraction, and interference all fitted comfortably into the classical picture, but one problem refused to cooperate. It came from something called blackbody radiation. A blackbody is an idealized object that absorbs all electromagnetic radiation falling upon it, and, when heated, emits radiation with a spectrum determined by its temperature. Real objects can approximate this behavior closely enough for the underlying physics to be measured. The difficulty was that classical physics gave the wrong answer for how much energy should be emitted at very short wavelengths. According to the classical calculation, the amount of energy should rise dramatically as the wavelength became shorter. Taken literally, the prediction suggested that a heated object would radiate an absurd amount of energy at high frequencies. Nature did nothing of the sort. Experiments showed that the emitted spectrum rises to a peak and then falls away again at shorter wavelengths. In 1900, Max Carl Ernst Ludwig Planck found a mathematical way to reproduce the observed spectrum. His solution required something radical. energy could not be exchanged in completely arbitrary amounts. Instead, it had to come in discrete portions related to the frequency of the radiation. The relationship can be written in words as energy equals Planck's constant multiplied by frequency. Planck's constant is extremely small on ordinary human scales, which is one reason quantum behaviour is usually hidden in everyday life. But at atomic scales, it becomes fundamental. Planck initially introduced quantization as part of the mathematics describing how matter exchanged energy with radiation. The truly dramatic step came a few years later. In 1905, Albert Einstein applied the idea more directly to light itself. He was trying to explain the photoelectric effect. When light shines on certain materials, electrons can be knocked out of the surface. Classical wave theory seemed to suggest that increasing the intensity of the light should eventually provide enough energy to eject electrons, regardless of the frequency. But experiments showed something different. Below a certain threshold frequency, increasing the intensity did not solve the problem. You could shine brighter and brighter low-frequency light onto the material, and still no electrons would be emitted. Yet sufficiently high-frequency light could eject electrons even when its intensity was quite low. Einstein explained this by proposing that light transferred energy in discrete packets. Each packet carried an amount of energy determined by the frequency of the light. A higher frequency packet carried more energy than a lower frequency one. If one packet did not carry enough energy to overcome the binding of an electron within the material, making the beam brighter simply supplied more inadequate packets. More of the wrong-sized payment did not suddenly make one payment large enough. But once the frequency crossed the necessary threshold, individual interactions could transfer enough energy to release electrons. This idea transformed the meaning of quantization. Light was not merely interacting with matter in a way that happened to produce discrete results. The radiation itself appeared to possess discrete energy units. Robert Andrews Millikan later tested Einstein's photoelectric relation with great care. Interestingly, Millikan initially doubted Einstein's interpretation, but his measurements confirmed the predicted relationship between the frequency of the incoming light and the maximum kinetic energy of the emitted electrons with impressive accuracy. The experiments supported the equation even before everyone was comfortable with what it seemed to mean. And what it meant was difficult to ignore. The classical electromagnetic wave had not become useless. It still explained an enormous range of phenomena, but it was no longer enough by itself. Light could interfere and diffract like a wave, yet when it exchanged energy with matter, those exchanges could occur in discrete amounts. The old choice between wave and particle had begun to break down. Physics was moving toward a stranger description in which light could retain its wave behaviour while also arriving in individual quantum units. Those units would eventually become known as photons. The word photon gives us a useful name for the smallest quantum unit of electromagnetic radiation, but it can also tempt us into imagining something that quantum physics does not actually describe. A photon is not thought of as a tiny glowing sphere racing through space. It has no known surface, no little shell, and no experimentally established internal machinery. In modern physics, the photon is treated as an elementary quantum associated with the electromagnetic field. That word elementary matters. It means that, as far as current experiments can tell, the photon is not made from smaller constituent particles. It is one of the basic entities used in the standard model of particle physics. One of the most important properties of a photon is its energy. The relationship is simple enough to say aloud. The energy of a photon equals Planck's constant multiplied by its frequency. This means that frequency is directly tied to how much energy each photon carries. Higher frequency radiation is made up of photons with more energy. Lower frequency radiation is made up of photons with less energy. In vacuum, frequency and wavelength are inversely related. As frequency rises, wavelength becomes shorter. As frequency falls, wavelength becomes longer. So short wavelength radiation, such as X-rays and gamma rays, involves much more energetic photons than radio waves. Visible light sits somewhere in between. Even within the visible range, violet and blue photons carry more energy individually than red photons because they have higher frequencies. But energy is not the only thing a photon can carry. It also carries momentum. That became especially clear through the work of Arthur Holly Compton in the early 1920s. Compton studied what happened when X-rays scattered from electrons. If light were only a smooth classical wave, the details of the scattering were difficult to explain. But if the incoming X-ray behaved as though it delivered energy and momentum in a discrete interaction, the results made sense. The wavelength of the outgoing radiation changed in a way that matched the idea of a photon colliding with an electron and transferring some of its energy and momentum. This became known as the Compton effect. It provided strong evidence that light could behave in a distinctly particle-like way. For a photon, momentum is related to energy through another simple relationship. Photon momentum equals photon energy divided by the speed of light. This may sound slightly odd, because photons have zero rest mass. But zero rest mass does not mean zero energy. And it does not mean zero momentum. In relativity, mass, energy and momentum are related, but they are not the same thing. A photon can therefore push on matter. Light can exert radiation pressure. This effect is usually tiny in everyday situations, but it is real and measurable. It is also the principle behind ideas such as solar sails, where sunlight can gradually transfer momentum to a reflective surface in space. Photons are also unusual because they never have a valid rest frame. For a massive object, you can always imagine travelling alongside it so that, relative to you, it is momentarily at rest. You cannot do that with a photon. In vacuum, light always propagates locally at the speed of light. There is no physical reference frame in which you can sit beside a photon and watch it hovering motionless. That alone should make us cautious about picturing it as an ordinary little object. The photon behaves enough like a particle to transfer energy in discrete amounts. It behaves enough like a particle to carry momentum. Detectors can register individual photon events, and yet the photon does not behave like a miniature classical bead. It remains a quantum object. Its behaviour can include interference, superposition, and other effects that do not fit neatly into the classical particle picture. So when we say that light arrives in quantum packets, the word packet is useful, but only up to a point. A photon is not a tiny parcel with something packed inside it. It is the smallest discrete excitation of the electromagnetic field that can appear in a simple one-photon state. And that makes it both more precise and far stranger than the old image of tiny particles of light flying through empty space. The idea of the photon gives us a useful way to talk about light, but quantum field theory takes us one step deeper. Instead of imagining the universe as a collection of tiny particles moving through an otherwise empty stage, quantum field theory describes nature in terms of fields that extend throughout space. The electron is associated with an electron field. Quarks are associated with quark fields. And light is associated with the electromagnetic field. In this description, particles are not separate little objects sitting on top of the fields. They are excitations of those fields. The electromagnetic field can exist in many different quantum states. In some of those states, the field carries discrete units of excitation that we identify as photons. So when a detector registers a photon, quantum field theory does not require us to imagine a tiny glowing pellet arriving from somewhere. Instead, we can describe the event as an interaction involving the quantum electromagnetic field and the quantum fields that make up the detector. This way of thinking emerged gradually as physicists tried to combine quantum mechanics with the principles of relativity. Paul Adrian Maurice Dirac played a major role in this development. In the late 1920s, Dirac developed one of the earliest successful quantum descriptions of the electromagnetic field and showed how the emission and absorption of light could arise naturally within that framework. This was a profound shift. Earlier quantum theory often treated photons almost as though they were individual objects being added to an otherwise classical electromagnetic picture. Quantum field theory made the field itself quantum mechanical. One useful way to understand the idea is to imagine the electromagnetic field as having many possible modes. A field mode is a particular possible pattern of electromagnetic oscillation. It can be characterized by properties such as frequency, direction of propagation, and polarisation. Each mode can be treated mathematically in a way that resembles a quantum harmonic oscillator. A classical harmonic oscillator might be something like a mass moving back and forth on a spring. The quantum version can possess energy only in certain discrete amounts. The analogy is useful, but it should not be taken too literally. The electromagnetic field is not a material substance wobbling around like jelly, and there are no microscopic springs hidden inside empty space. The comparison is mathematical. It tells us that the energy stored in each allowed field mode is quantist. Adding one quantum of excitation to a particular electromagnetic mode corresponds to creating one photon in that mode. Removing one quantum corresponds to annihilating a photon. The words creation and annihilation can sound dramatic, but in quantum field theory they are perfectly ordinary processes. A photon can be created when an atom loses energy. A photon can be absorbed when matter gains energy. The number of photons is therefore not fixed forever. Photon number is a property of the quantum state of the electromagnetic field. That distinction matters. In everyday language, saying that light is made of photons is usually good enough, but the deeper quantum field description is more subtle. A beam of light is not necessarily best imagined as a bag containing a definite collection of permanent little objects. Different quantum states of the electromagnetic field can have very different properties. Some states contain a definite number of photons. Others, including states that closely resemble familiar classical light waves, do not have one exact photon number at all. This is why the phrase light is made of photons is helpful, but incomplete. Photons are real features of the theory and real units in which electromagnetic energy can be detected and exchanged, but they arise from the quantum electromagnetic field. As far as established physics can currently tell, the photon itself is not known to be built from smaller constituent particles. There is no confirmed internal structure hiding beneath it. The deeper description is the field. And that brings the central question into much sharper focus. What we call light is not fundamentally a stream of tiny glowing objects moving through empty space. It is the behaviour of the quantum electromagnetic field. Photons are the discrete excitations through which that field can carry energy, momentum, and other quantum properties. So when light crosses a room, leaves a distant star, or arrives at a detector, quantum physics describes something much stranger than a miniature object simply travelling from one place to another. It describes a quantum field changing state. The strangest thing about calling light a particle is that it never stopped behaving like a wave. Thomas Young's interference experiment had already shown that light could produce the bright and dark bands expected from overlapping waves. Quantum physics did not erase that result. Instead, it made the result more peculiar. If light is sent through a double slit one photon at a time, each photon is eventually detected at one particular location. There is no faint smear across the detector. There is a single event. Then another. Then another. At first, those individual detections can look almost random, but after enough photons have arrived, a pattern begins to emerge. Bright regions appear where many detections accumulate. Dark regions remain where very few appear. Eventually, the same interference pattern associated with waves becomes visible. This is one of the clearest reasons why a photon cannot be understood as an ordinary classical particle following one definite path like a tiny bead. Quantum mechanics describes the situation using probability amplitudes. A probability amplitude is not quite the same thing as an ordinary probability. Different possible alternatives can be assigned amplitudes, and those amplitudes can combine. When they reinforce one another, the probability of a particular outcome increases. When they cancel, the probability decreases. That ability to reinforce and cancel is what allows interference to appear. The important point is that quantum mechanics does not usually assign the photon a hidden little classical route, and then simply admit that we do not know which route it took. Instead, the quantum state contains the possible alternatives in a way that allows their amplitudes to interfere. That distinction is crucial. Ordinary uncertainty would mean the photon really took one path, but we happen not to know which one. Quantum interference is richer than that. The possible paths contribute together to the probabilities of later measurement outcomes. This is why asking which slit the photon truly passed through can become a surprisingly difficult question. If an experiment is arranged so that information about the path becomes available, the interference pattern can disappear. If that path information is not available, the alternatives can remain coherent and interfere. The photon therefore cannot be treated as a classical object quietly choosing one route, while the experimenter simply remains ignorant. At the same time, when the photon is absorbed by a detector, the energy transfer is localized. One detector element responds. One atom or group of atoms begins the amplification process that produces a measurable signal. So the quantum state can be spread across a region, while the eventual detection occurs at a particular place. That combination is part of what makes light so difficult to squeeze into familiar categories. The phase of the quantum state is also essential. Interference does not depend only on how many photons are present. It depends on the relative phase between different components of the electromagnetic quantum state. Phase determines whether amplitudes reinforce one another or cancel. This is closely related to the phase of classical electromagnetic waves. But quantum theory extends the idea into situations where individual photon detections are involved. For this reason, the phrase wave-particle duality can be useful, but it can also encourage the wrong picture. It is tempting to imagine that a photon changes costume. Sometimes it decides to be a particle. Sometimes it decides to be a wave. That is not really what quantum theory says. The photon is always a quantum object. Wave-like and particle-like are classical descriptions that capture different parts of its behaviour. Discrete energy transfer looks particle-like. Interference looks wave-like. Neither picture on its own is complete. The classical electromagnetic wave is therefore not simply discarded when quantum physics arrives. It reappears as an important limiting behaviour of certain quantum states of the electromagnetic field. When enormous numbers of photons occupy suitable states, the field can behave very much like the smooth electromagnetic waves described by James Clerk Maxwell. At very low light levels, the discrete quantum character becomes impossible to ignore, so the wave description and the photon description are not competing stories where one must eventually defeat the other. They are different aspects of a deeper framework. A photon can produce a localized detection while belonging to a quantum state whose probability amplitudes spread out and interfere. That is not a failure of the theory to decide what light is. It is part of what light actually is in quantum physics. One of the easiest mistakes to make when thinking about a photon is to imagine a very small object with a very small shape. Perhaps a tiny sphere, perhaps something like a microscopic bead of light. That picture is understandable, because our everyday idea of a particle is usually tied to objects that occupy a definite region of space and have a surface. Quantum field theory does not describe a photon that way. A photon is not assigned a rigid physical radius, a hard outer boundary, or a miniature internal shape. According to the standard model of particle physics, the photon is elementary. That means there is currently no experimental evidence that it is built from smaller constituent particles. A proton has internal structure. It contains quarks and gluons. A photon, by contrast, has no experimentally established components sitting inside it. This sometimes leads people to say that the photon is point-like. But even that phrase needs care. In particle physics, describing something as point-like often means that experiments have found no measurable internal size or substructure down to the scales being tested. It does not necessarily mean that the photon should be pictured as a literal mathematical dot travelling along a perfectly defined classical path. That distinction becomes especially important when we ask where a photon actually is. For an ordinary non-relativistic massive particle, quantum mechanics allows us to define position in a fairly familiar way. The mathematics of photon position is much more subtle. Because photons are massless relativistic excitations of the electromagnetic field, there is no simple photon position operator that behaves in exactly the same way as the position operator for a non-relativistic particle such as an electron in basic quantum mechanics. This does not mean that photons cannot be detected at particular places. They certainly can. A single photon can be absorbed by a detector at one localized region, producing one discrete detection event. But before that detection, the quantum state associated with the photon may be spread over a much larger region. That spread should not be confused with the physical diameter of a tiny object. It describes the spatial structure of the quantum state. A photon prepared in one experiment may have a state concentrated within a relatively short region. Another photon may be described by a state extending over a much greater distance. So the question of how large a photon is does not have one universal classical answer. A useful way of describing a photon that is concentrated within a finite region is through a wave packet. A perfectly monochromatic wave has one exact frequency and one exact wavelength. But such a wave would extend indefinitely through space. It would have no sharply defined beginning or end. Real photon states can instead be constructed from a range of frequencies and wavelengths. These different components combine to form a wave packet that is more localized. The narrower we try to make that packet in space, the broader the range of frequencies or momenta generally has to become. This is connected to the uncertainty relationships of quantum mechanics. A state that is extremely well localized cannot at the same time possess an arbitrarily precise momentum. Likewise, restricting a pulse to a short duration requires a spread of frequencies rather than one perfectly exact frequency. This is not a defect in our measuring equipment. It is built into the structure of quantum states. The same idea can be seen with an ordinary pulse of light. A very long, nearly monochromatic pulse can be described using a very narrow range of frequencies. A very short pulse requires many frequencies combined together. The spatial extent of the light, therefore, depends on how the electromagnetic field has been prepared. This makes the phrase size of a photon rather dangerous if it is treated like the size of a grain of sand. There is no known photon surface that could be measured from one side to the other. There is no confirmed little sphere whose diameter remains fixed as it travels. Instead, there is a quantum state of the electromagnetic field with a certain spatial and momentum structure. That state may be broad, it may be narrow. It may extend across a considerable distance and still deposit one quantum of energy at one detector location when an interaction occurs. This is one of the places where classical intuition begins to run out of useful pictures. A photon can behave as though it is point-like in an interaction, because energy and momentum can be exchanged in a localized event. At the same time, the quantum state associated with that photon can be distributed across space. Those two statements are not contradictory. They simply describe different aspects of the same quantum object. So asking how large a photon is sounds like a straightforward question, but it quietly assumes that a photon should resemble a tiny classical object with a fixed shape. Quantum physics gives us no reason to expect that. The photon has no known internal radius, no rigid boundary, and no experimentally established smaller pieces. Its spatial extent is instead tied to the quantum state in which it has been prepared. And once again, the deeper we look at light, the less it resembles anything we can comfortably hold in the palm of a hand. Colour feels like one of the most obvious properties of light. Red light looks red. Blue light looks blue. Sunlight can appear white. A rainbow separates that light into a familiar sweep of colours. But quantum physics gives us a slightly different way to think about what colour actually is. Light belongs to the electromagnetic spectrum. This spectrum is a continuous range of electromagnetic frequencies extending far beyond anything the human eye can detect. At the low frequency end are radio waves. Moving upward in frequency, we encounter microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and eventually gamma rays. All of these are manifestations of the same electromagnetic field. They are not fundamentally different substances. What changes is primarily the frequency and wavelength of the electromagnetic radiation, and therefore the energy carried by individual photons. Visible light occupies only a very narrow slice of this enormous spectrum. Human vision is sensitive to wavelengths roughly between about 700 nanometers at the red end and around 400 nanometers at the violet end, although the boundaries are gradual rather than perfectly sharp. That means most electromagnetic radiation in the universe does not correspond to any visible colour at all. A radio photon is not an extremely deep shade of red. An X-ray photon is not an unimaginably bright violet. Those frequencies simply lie outside the range that the human visual system interprets as colour. The energy of a photon is directly connected to its frequency. The energy of a photon equals Planck's constant multiplied by its frequency. So, a photon with a higher frequency carries more energy than one with a lower frequency. Within visible light, blue and violet photons therefore carry more energy individually than red photons. The difference is not enormous by everyday standards, but it matters greatly in atomic and molecular interactions. Shorter wavelength visible light corresponds to higher frequency and higher photon energy. Longer wavelength visible light corresponds to lower frequency and lower photon energy. It is tempting to say that this frequency simply is the colour, but even that is not quite the full story. Frequency and wavelength are physical properties of electromagnetic radiation. Colour is a perception produced when that radiation interacts with a visual system. In the human eye, light reaches the retina and interacts with specialized photoreceptor cells. Among these are cone cells, which come in different types with different sensitivities across the visible spectrum. The response of those cone cells is processed by networks of neurons in the retina and then by the brain. What we experience as colour emerges from that biological processing. So a photon does not contain a tiny drop of blue or red substance. There is no microscopic paint hidden inside it. A photon can have a particular energy, frequency, momentum, polarisation, and quantum state. Colour, however, is the perceptual experience that can arise when certain distributions of visible photons interact with the eye and brain. This distinction becomes especially clear when we consider white light. White light is not associated with one unique photon frequency. It can be produced by combining a broad range of visible wavelengths. The sun, for example, emits electromagnetic radiation over a wide spectrum, and the mixture reaching our eyes can be perceived as approximately white under many conditions. Magenta provides an even more interesting example. There is no single wavelength of visible light that corresponds uniquely to magenta. Instead, magenta can be perceived when the visual system receives a combination of light that strongly stimulates responses associated with the red and blue ends of the visible spectrum without the same response in between. The brain turns that combination into a colour experience. So colour does not map perfectly onto one photon frequency. Sometimes it does so approximately, as with nearly monochromatic light. Sometimes it arises from mixtures of many frequencies. The physical spectrum and the perceived colour are closely related, but they are not identical. This becomes extraordinarily useful in astronomy. Light arriving from a distant star or galaxy may have travelled for years, millions of years, or even billions of years before reaching a telescope. Yet the distribution of photon frequencies can carry detailed information about the place where that light originated. A hot object tends to produce a different thermal spectrum from a cooler one. Atoms and molecules can absorb or emit photons at characteristic frequencies associated with their quantum energy levels. These patterns appear as spectral lines. By studying them, astronomers can identify chemical elements in distant stars. Hydrogen leaves characteristic features. Helium leaves others. So do sodium, calcium, iron, oxygen, and many more elements. The positions of those spectral features can also shift if the source is moving relative to us. A shift toward longer wavelengths can indicate recession. A shift toward shorter wavelengths can indicate approach. Spectra can therefore reveal composition, temperature, motion, density, magnetic effects, and other physical conditions in places far beyond any direct human reach. A photon arriving at a telescope may seem almost impossibly small and simple, yet its frequency can become part of a much larger pattern carrying information across the universe. And what we eventually call colour is only one small human interpretation of that much broader electromagnetic reality. Light is not made of colour. Colour is something that certain forms of light can become when they meet a mind capable of seeing them. Light carries more information than brightness and colour alone. It also has a property called polarisation. In classical electromagnetism, light is described as an electromagnetic wave made from oscillating electric and magnetic fields. These fields are oriented in particular directions as the wave travels. For a simple linearly polarized wave, the electric field oscillates back and forth along one fixed direction, while the magnetic field oscillates at right angles to it. That orientation is what we call polarisation. Unpolarized light, such as ordinary sunlight before it has been filtered or reflected in particular ways, contains many different polarization orientations mixed together. Quantum physics keeps the idea of polarization, but gives it a deeper meaning. An individual photon can possess a polarization state. This does not mean that a tiny arrow is physically painted onto the photon. Instead, polarization is part of the quantum state, describing how that photon can interact with matter and with measurement devices. The photon also possesses an intrinsic quantum property called spin. The photon is classified as a spin 1 particle. That phrase can be misleading if it is interpreted too literally. The photon is not a tiny spinning ball rotating around an internal axis. Quantum spin is not ordinary mechanical rotation. It is an intrinsic form of angular momentum built into the mathematical description of elementary particles. A photon carries angular momentum even though there is no little spherical object physically turning inside it. For photons travelling freely through vacuum, another useful concept is helicity. Helicity describes the relationship between a particle's spin and its direction of motion. A free photon has two physical helicity states. These can be associated with right-handed and left-handed circular polarization. Circular polarization can be pictured classically by imagining the direction of the electric field rotating as the light moves forward. From the quantum viewpoint, the corresponding photon can occupy one of two helicity states. This is connected to an important fact about the photon. Because the photon is massless, it has only two physical polarization states for free propagation. A hypothetical massive spin 1 particle would have three spin polarization possibilities. Along with two transverse states, it could possess a longitudinal state aligned with its direction of motion. An ordinary free photon does not have that physical longitudinal polarization. Its two physical polarization states are transverse to its direction of propagation. That difference is closely tied to the mathematical structure of electromagnetism and to the fact that the photon has no rest mass. There are several familiar ways of describing photon polarization. Light can be linearly polarized. It can be circularly polarized. Or it can be elliptically polarized. These are not different species of photon. A linearly polarized photon is not made from different material than a circularly polarized one. They are different quantum states of the same underlying electromagnetic field, and these states can be related through quantum superposition. For example, a state of linear polarization can be represented as a particular superposition of two circular polarization states. Likewise, circular polarization can be described using suitable combinations of linear polarization states. This becomes especially clear in experiments involving polarizing filters. Suppose a photon is prepared with one linear polarization and sent toward a filter oriented at a different angle. Quantum mechanics does not always say that the photon secretly possesses one definite answer to every possible polarization measurement before the measurement is made. Instead, its state can be a superposition relative to the basis being measured. The possible outcomes have quantum amplitudes. The photon may pass through the filter or be absorbed, with probabilities determined by the relationship between its prepared polarization state and the orientation of the filter. Beam splitters designed to separate different polarization states can perform a similar role. A single photon entering such a device can be described by a quantum state containing multiple possible outcomes. If those alternatives remain coherent, they can later interfere. So even something as apparently straightforward as the direction of polarization leads us directly back into the central principles of quantum mechanics. Superposition, probability amplitudes, measurement, and quantum state. Polarisation is also important because it points towards something deeper in the theory of electromagnetism. The photon is not merely a convenient particle added on top of James Clerk Maxwell's classical theory. In modern particle physics, it is understood as a gauge boson associated with electromagnetic gauge symmetry. That underlying gauge structure helps explain why the photon has the properties it does, including the pattern of physical polarisation states available to a massless spin 1 particle. The mathematics becomes more advanced at that level, but the physical lesson is simple. The photon is not characterized only by its energy or its direction of travel. Its quantum state contains additional structure. Frequency matters, momentum matters, polarization matters, spin matters, helicity matters. But none of these properties should be mistaken for ingredients hidden inside the photon. Spin is not a smaller spinning component. Polarization is not an internal strip of material. Helicity is not a mechanism tucked away beneath the surface. They are intrinsic properties and state descriptions belonging to the photon as a quantum excitation of the electromagnetic field. So when we ask what light is made of, quantum physics keeps offering the same gentle correction to our everyday intuition. The deeper we examine a photon, the less it resembles a tiny object containing smaller parts. What we find instead is a remarkably rich quantum state, described not by an internal shape, but by the fundamental properties of the electromagnetic field itself. Light becomes especially interesting when it meets matter. A photon can travel across empty space for millions or even billions of years, then suddenly encounter an electron, an atom, or a piece of material and transfer energy or momentum in a very precise way. The theory that describes these interactions is called quantum electrodynamics. Quantum electrodynamics is the quantum field theory of the electromagnetic interaction. It describes how the electromagnetic field interacts with electrically charged quantum fields, especially the electron field and the positron field. This immediately changes the picture from something like tiny charged balls simply throwing photons back and forth. In quantum field theory, electrons are excitations of the electron field. Positrons are excitations of the corresponding antimatter states of that same relativistic field. Photons are excitations of the electromagnetic field. And electromagnetic interactions occur because these fields are coupled to one another. One of the major steps toward this description came from Paul Adrien Maurice Dirac. Dirac developed a relativistic quantum theory of the electron in the late 1920s. His equation combined quantum mechanics with special relativity and led to something extraordinary. The mathematics contained solutions that eventually came to be understood as evidence for antimatter. The positron, the antimatter counterpart of the electron, was later discovered experimentally. This was a major clue that relativistic quantum physics required a richer description than one in which a fixed number of ordinary particles simply moved around forever. The modern form of quantum electrodynamics emerged through the work of several physicists, especially Shinichiro Tominaga, Julian Seymour Schwinger, and Richard Phillips Feynman. They developed methods for dealing with a serious mathematical difficulty that appeared when physicists tried to calculate electromagnetic interactions at very small scales. Early calculations sometimes produced infinite quantities. That is rarely a reassuring result when the quantity being calculated is supposed to correspond to something measurable. The solution involved a procedure known as renormalization. Renormalization allows the theory to be expressed in terms of physically measured quantities such as the electron's mass and electric charge, while systematically handling the troublesome infinities that appear in intermediate calculations. The resulting theory became extraordinarily successful. To visualize and organize these calculations, Richard Phillips Feynman introduced what are now called Feynman diagrams. These diagrams often show lines meeting at points. An electron line may approach an interaction point, a photon line may connect to it, and another electron line may continue away. It is very tempting to look at such a picture and imagine that it is literally showing what happened. But a Feynman diagram is not a photograph of microscopic reality. It is a bookkeeping device. Each diagram represents a particular mathematical contribution to the probability amplitude for a physical process. The lines are not necessarily little trails through space followed by particles. The diagram helps physicists organize terms in a calculation. This becomes particularly important when discussing virtual photons. A real photon can be prepared as incoming radiation or detected as outgoing radiation. Sunlight arriving at a detector involves real photons. A photon emitted by an excited atom and later absorbed by another system can be treated as a real photon. Virtual photons are different. They appear inside certain mathematical descriptions of interactions, especially perturbative calculations using Feynman diagrams. They are internal elements of the calculation and cannot be directly detected as free incoming or outgoing particles. It is common to hear that electromagnetic forces happen because charged particles exchange virtual photons. That language can be useful, but it becomes misleading if virtual photons are imagined as ordinary detectable particles secretly racing between charges. They are not small hidden flashes that briefly break the laws of physics before disappearing. They are features of a particular mathematical expansion used to calculate quantum interactions. The strength of quantum electrodynamics is not merely philosophical. It makes extremely precise experimental predictions. One famous example involves the magnetic properties of the electron. Quantum electrodynamics predicts tiny corrections to the electron's magnetic behaviour caused by interactions with the quantum electromagnetic field. Measurements and calculations agree to an astonishing degree of precision. This makes quantum electrodynamics one of the most accurately tested theories in all of physics, and that success tells us something important about light itself. Light cannot be completely understood in isolation from matter. The photon belongs to the electromagnetic field, but the meaning of electromagnetic interaction emerges from the way that field couples to charged fields such as the electron field. Emission, absorption, scattering, reflection, and many other familiar behaviours of light all come from these interactions. So a photon is not merely a tiny messenger moving between pieces of matter. It belongs to a network of interacting quantum fields. The electromagnetic field carries its own excitations. The electron field carries others, and what we experience as light interacting with matter is the result of those fields influencing one another according to the rules of quantum electrodynamics. That broader picture brings us even closer to the modern answer. Light is not simply something travelling through a universe made from other things. It is one part of the same interconnected quantum field structure from which matter itself is described. Atoms do not simply absorb and release light in any amount they please. At the quantum level, their behaviour is much more selective. Electrons bound inside atoms can occupy only certain allowed energy states. They cannot settle at every imaginable energy in between. This was one of the great clues that classical physics was missing something fundamental. An early step toward understanding it came from Niels Henrik David Bohr. Bohr proposed that electrons in atoms could occupy only certain permitted energy levels. In his model, electrons moved in fixed orbits around the nucleus, and transitions between those orbits were associated with the absorption or emission of light. The model was historically important because it captured the idea of discrete atomic energies, but the picture of electrons circling the nucleus like tiny planets did not survive. Modern quantum mechanics replaced those fixed paths with quantum states. Erwin Rudolf Joseph Alexander Schrödinger developed wave mechanics, which allowed the electron in an atom to be described using a wave function. The solutions of the Schrödinger equation for an atom produce allowed quantum states with particular energies. These states are associated with atomic orbitals. An orbital is not a miniature track showing where an electron travels. It describes the spatial structure of the electron's quantum state and the probabilities associated with measurements of its position. The important point is that the allowed energies remain quantist. An electron bound in an atom may occupy one allowed energy state and later transition to another. When the atom moves from a higher energy state to a lower one, the energy difference can be transferred to the electromagnetic field. A photon can then be emitted. The photon's energy corresponds to the difference between the initial and final atomic energy states. If the difference is larger, the emitted photon has a higher frequency. If the difference is smaller, the photon has a lower frequency. This is why atoms do not generally emit every possible color or frequency of light. Their internal quantum structure restricts the transitions that can occur. Absorption works in the opposite direction. A photon arriving at an atom can transfer energy to the atomic system if the interaction is allowed and the photon's energy matches an accessible transition closely enough. The atom can then move into a higher energy state. But not every photon will be absorbed. Its energy, the quantum states involved, the polarisation of the light, and specific selection rules can all influence whether a transition is permitted or strongly suppressed. This gives atomic interactions a remarkable degree of precision. There are also different ways in which emission can happen. One is spontaneous emission. An atom in an excited state can decay to a lower energy state without an incoming photon triggering the event, releasing a photon as the electromagnetic field gains one quantum of excitation. The exact time at which a particular spontaneous emission event occurs is not generally predicted deterministically by quantum theory. Instead, the theory provides probabilities and characteristic decay rates. Another process is stimulated emission. Albert Einstein identified the importance of this mechanism while studying the interaction between radiation and matter. If an atom is already in an excited state, an incoming photon of the appropriate energy can stimulate the atom to transition downward. A second photon is then emitted in a state closely related to the stimulating radiation. This process lies at the heart of the laser. In a laser, many atoms or other quantum systems are arranged so that stimulated emission can repeatedly amplify electromagnetic radiation. The result can be highly coherent light with a narrow range of frequencies and a well-defined direction. Atomic emission and absorption also produce one of the most beautiful pieces of evidence for quantization. Spectral lines. When light from excited atoms is separated by wavelength, it often appears as a set of distinct lines rather than a smooth rainbow. Each line corresponds to particular allowed transitions between quantum energy states. Different elements have different atomic structures, so they produce different patterns of spectral lines. Hydrogen has one characteristic pattern, helium has another. Sodium, iron, calcium, oxygen, and other elements each carry their own spectral signatures. These patterns are so distinctive that astronomers can identify elements in distant stars by analysing the light that reaches Earth. The light may have travelled for hundreds, thousands, or millions of years, yet its frequencies still preserve information about the quantum transitions that produced or absorbed it. There is also a deeper lesson hidden inside these processes. Photons are not little objects stored inside atoms, waiting patiently to be released. An excited atom does not contain a bag of photons. When emission occurs, the quantum state of the combined matter and electromagnetic field changes. A photon is created as the electromagnetic field gains a quantum of excitation. When absorption occurs, that excitation can disappear as energy is transferred into the atom. Photon number can change. Energy and momentum remain conserved, but the individual photon need not exist permanently before and after the interaction. This is exactly what we would expect if photons are excitations of a quantum field rather than indestructible microscopic pieces of substance. Atoms do not merely reveal that light comes in discrete amounts. They show how those amounts can be created, absorbed, and transformed through the interaction of quantum fields. Photons behave in a way that would be very strange for an ordinary piece of matter. They can be created, they can be absorbed, and they can disappear entirely from a process without anything mysterious being lost. The key is that photon number itself is not fundamentally conserved. There is no rule requiring the universe to contain exactly the same number of photons from one moment to the next. What must still be conserved are quantities such as total energy and momentum, along with any other relevant conserved quantum properties. This fits naturally with the quantum field picture. A photon is an excitation of the electromagnetic field, not an indestructible grain of substance that must exist forever. Photons can be produced in many different ways. An atom dropping from a higher energy state to a lower one can emit a photon. A hot object can produce enormous numbers of photons through thermal radiation. Electrical discharges can accelerate charged particles and generate light. Electrons travelling through magnetic fields can emit synchrotron radiation. Charged particles that are rapidly slowed or deflected can produce Bremsstrahlung, a form of electromagnetic radiation whose name comes from the German term for breaking radiation. In every case, the electromagnetic field can gain new excitations. Those excitations are what we call photons. The reverse can happen just as naturally. A photon can be absorbed by an atom, molecule, solid surface, detector, or other quantum system. Its energy and momentum are transferred into that system. The photon is no longer present as an outgoing excitation of the electromagnetic field. Nothing has vanished from physics. The energy has simply changed form. One of the clearest examples of this flexibility appears in the relationship between matter and antimatter. An electron and a positron have the same mass but opposite electric charge. When they meet under suitable conditions, they can annihilate. The word annihilation sounds as though something has been destroyed without trace, but that is not what happens. Their mass energy and kinetic energy are converted into other forms, often photons. If the electron and positron are initially close to rest relative to one another, a common outcome is the production of two gamma-ray photons travelling in opposite directions. Two photons are needed in that simple situation so that total momentum can be conserved. The massive particles disappear as electron and positron excitations, while electromagnetic excitations appear instead. There is also a reverse type of process. A sufficiently energetic photon can contribute to the creation of an electron and a positron. This is called pair production. But the conditions matter. A single photon travelling through completely empty space cannot simply turn itself into an electron and a positron. Energy alone is not enough. Momentum must also be conserved. There is no way for one freely travelling photon in vacuum to produce the two massive particles while satisfying both conservation laws by itself. Pair production can occur near an atomic nucleus, for example, because the nucleus can recoil and take part in balancing the momentum. Photon-photon interactions can also produce particle pairs when the combined energy is sufficiently high and the geometry allows energy and momentum to be conserved. This reveals something important about what photons really are. They do not behave like permanent microscopic building blocks, in the same way we might imagine a collection of tiny stones. A stone can be moved from one place to another, but it remains the same stone. Photons are different. They can be created when the electromagnetic field gains excitation. They can be destroyed when that excitation is transferred elsewhere. The field remains, the energy remains accounted for, but the number of photons can change. This is why it is slightly misleading to imagine every beam of light as a stream of eternal particles that were manufactured somewhere and must continue existing forever. A photon may be emitted from an atom, travel across space, and later be absorbed completely. Its existence as a photon can begin and end at interactions. Detectors still register light in discrete events. One photon can deposit one quantum of electromagnetic energy, another can arrive later. That discreteness is real, but it does not mean that photons are indestructible microscopic grains. Quantum field theory gives a more flexible picture. Particles are excitations that can appear and disappear when interactions allow it. Light can become matter. Matter can become light. And throughout these transformations, the deeper rules of conservation remain intact. The photon is therefore not a permanent object that the universe must keep track of forever. It is a temporary, measurable excitation of the electromagnetic field, capable of carrying energy and momentum for as long as the physical situation allows. There is a curious gap between the way light behaves at the quantum level and the way it appears in everyday life. Quantum physics tells us that electromagnetic energy can be exchanged in discrete units called photons, and yet ordinary light does not usually look grainy. A beam from a lamp appears smooth. Sunlight spreads continuously across a wall. James Clerk Maxwell's classical theory describes light as a smoothly varying electromagnetic wave, with electric and magnetic fields changing continuously through space and time. So how does that smooth classical picture emerge from a theory built from quantum excitations? The answer depends on the quantum state of the electromagnetic field. Not all light is in the same kind of state. A single photon state, thermal light, and laser light can all involve the same electromagnetic field while behaving very differently. One of the physicists who helped clarify this was Roy J. Glauber. Glauber developed much of the modern quantum theory of optical coherence, providing a framework for describing how different quantum states of light produce different statistical and interference properties. This made it possible to connect the language of photons with the familiar behaviour of classical electromagnetic waves in a much more precise way. A particularly important example is the coherent state. A coherent state is a quantum state of the electromagnetic field that behaves, in many respects, very much like a classical electromagnetic wave. The expectation values of the electric and magnetic fields can oscillate in a smooth and regular fashion. That makes coherent states an excellent quantum description of idealized laser light. But there is an interesting twist. A coherent state does not contain one exact, fixed number of photons. Instead, if the number of photons were measured repeatedly in identically prepared coherent states, different measurements could produce different photon counts. Those counts follow a statistical distribution known as a Poisson distribution. There is an average photon number, but the exact number fluctuates around it. As that average becomes very large, the relative size of the fluctuations becomes small. so a beam containing an enormous average number of photons can appear extremely steady even though its exact photon number is not perfectly fixed. That is one reason classical behaviour emerges so naturally at large scales. Laser light is one of the clearest places to see this connection. In 1960, Theodore Harold Maiman demonstrated the first working laser. Lasers rely on stimulated emission, in which an electromagnetic field can encourage excited atoms or other quantum systems to emit additional radiation into suitable modes. The resulting light can be highly directional, concentrated within a narrow range of frequencies, and strongly coherent. Coherence means that the phase relationships within the light are unusually well organized. This is why laser beams can produce clean interference effects and remain tightly directed over long distances. But laser light is not simply a more intense version of every other kind of light. Thermal light, such as the glow from a hot object, has different statistical properties. Its photons are distributed among many modes with much less organized phase relationships. A carefully prepared single photon state is different again. So the word light covers a surprisingly broad family of quantum states. The underlying field is the same. What changes is how that field is excited. Experiments by Robert Hambry Brown and Richard Quentin Twiss helped reveal these differences. They studied correlations between light intensity measurements at different detectors. Their work showed that light contains statistical information that cannot be understood merely by measuring average brightness. Thermal light tends to show a phenomenon called photon bunching, where detection events are more strongly clustered in time than they would be for an ideal coherent state. Coherent light has different correlation statistics. Other specially prepared quantum states can display still more unusual behaviour. This allows physicists to distinguish forms of light that may look similar if judged only by their average intensity. The larger lesson is that classical electromagnetic waves do not disappear when quantum physics takes over. They emerge from particular quantum states of the electromagnetic field. When huge numbers of photons occupy suitable modes, and the quantum fluctuations are small compared with the overall field strength, the behaviour can become almost indistinguishable from the smooth waves predicted by James Clerk Maxwell. This is an example of the classical limit. Quantum theory remains underneath. Nothing has stopped being quantum. The individual interactions can still involve discrete exchanges of energy. Photon number can still fluctuate. Quantum uncertainty is still present. But at large scales, those details can become relatively tiny compared with the overall behaviour. A smooth beam of light is therefore not evidence that photons disappear when enough of them gather together. It is evidence that large quantum systems can produce behaviour that closely resembles classical physics. The wave and the photon are not two incompatible substances. They are two levels of description of the same electromagnetic field. One reveals the discrete structure of quantum interactions. The other emerges when vast numbers of excitations behave together in a sufficiently organized way. And the familiar beam of light shining quietly across a room is where those two descriptions meet. Even a region containing no light at all is not quite empty in the quantum description. In classical physics, a vacuum might be imagined as a perfectly empty stage. No particles, no matter, no radiation, nothing present except space itself. Quantum field theory gives a more subtle picture. The vacuum is defined as the lowest energy state of the quantum fields. That means the electromagnetic field does not disappear when there are no photons present. The field is still part of the physical description. A region can contain no real photons and still possess the electromagnetic field in its vacuum state. This distinction matters because a photon is not the same thing as the field itself. Photons are excitations of the electromagnetic field. The vacuum is what remains when those excitations are absent. But even the lowest energy state is not simply equivalent to a classical field sitting perfectly still. Quantum fields possess unavoidable fluctuations associated with their quantum nature. For each mode of the electromagnetic field, the mathematical structure resembles a quantum harmonic oscillator, and even in its lowest energy state, a quantum harmonic oscillator does not have exactly zero energy. This minimum contribution is often called zero-point energy. It is tempting to turn this into a colourful picture of tiny photons constantly popping into and out of existence. That image is common, but it is not a particularly careful description. The vacuum is not simply filled with ordinary detectable photons that appear for a moment and then vanish before anyone notices. Real photons can travel to detectors and be observed as incoming or outgoing radiation. Vacuum fluctuations refer instead to properties of the quantum state of the field itself. One famous effect connected with this quantum structure is the Casimir effect. In 1948, Hendrik Brucht Gerhard Casimir predicted that two closely spaced conducting plates could experience a force arising from the quantum electromagnetic field. The boundaries imposed by the plates alter which electromagnetic field modes are permitted in the region between them compared with the surrounding space. The resulting change in vacuum energy can produce a measurable force. This effect is sometimes explained by saying that virtual photons appear between the plates and push them together. That picture can be useful as an informal analogy, but it should not be mistaken for a literal movie of what is happening. The Casimir effect is more accurately understood through the quantum field and the way boundary conditions modify its allowed states. Another important clue came from atomic physics. Willis Eugene Lamb and Robert Curtis Rutherford measured a tiny difference between energy levels in hydrogen that the simplest form of relativistic quantum mechanics did not predict correctly. This became known as the Lamb shift. Quantum electrodynamics explained the shift by accounting for interactions between the electron and the quantist electromagnetic field. The effect helped demonstrate that the vacuum state and quantum field interactions can influence measurable atomic energies. The vacuum can also affect how electric charge behaves. Through a phenomenon called vacuum polarisation, the electromagnetic field interacts with charged quantum fields such as the electron field. These interactions slightly modify the effective electromagnetic interaction compared with the simplest classical expectation. The effect becomes especially important when physicists probe extremely small distances or very high energies. Even light can interact indirectly with light. Photons themselves carry no electric charge, so classical electromagnetism does not provide a simple direct photon-photon force. But quantum electrodynamics allows photons to scatter from one another through interactions involving charged particle fields. In one common description, the calculation contains a loop associated with charged particles such as electrons and positrons. The photons do not need to carry electric charge themselves. Their interaction is mediated through the charged quantum fields to which the electromagnetic field is coupled. This phenomenon is called light-by-light scattering. For many decades it remained an extremely difficult effect to observe directly because the probability is very small under ordinary conditions. High-energy particle collisions made the effect more accessible. At the European Organisation for Nuclear Research, experiments involving heavy ions have produced extremely intense electromagnetic fields. When large atomic nuclei pass close to one another at enormous speeds, their electromagnetic fields can effectively supply energetic photons. Measurements at the Large Hadron Collider have provided evidence for light-by-light scattering in these collisions, allowing a rare quantum electrodynamic process to be studied experimentally. The result is a useful reminder that the quantum vacuum is not simply a passive emptiness through which light travels. The electromagnetic field is present even when no real photons occupy a region. Its lowest energy state has quantum structure. That structure can influence forces, atomic energy levels, and interactions between electromagnetic fields. But none of this means that empty space should be imagined as crowded with ordinary photons hiding just beyond detection. The deeper picture is quieter than that. The field remains. Its quantum state remains. And what we casually call empty space is not the absence of physics. It is simply the electromagnetic field in one of its most fundamental states. Light moves through empty space at the fundamental speed set by nature, but when it enters glass, water, or another transparent material, something changes. The light no longer propagates through the material in exactly the same way it does through vacuum. This is often described by saying that light slows down. That description is useful, but it needs one important qualification. A free photon travelling through vacuum still propagates locally at the speed of light. What changes inside a material is the behaviour of the combined electromagnetic field and the matter through which it is moving. Glass is not empty. It contains atoms, and those atoms contain electrically charged electrons and nuclei. When an electromagnetic wave enters the material, its electric field interacts with those charges. The electrons in the material respond to the changing electric field. They do not usually break free and fly away. Instead, their quantum states and charge distributions are slightly disturbed by the incoming electromagnetic field. That response then contributes its own electromagnetic effect. The result is a collective interaction between the light and the material. On large scales, physicists describe this behaviour using the refractive index. The refractive index tells us how electromagnetic waves propagate through a particular medium compared with vacuum. For ordinary visible light, the refractive index of water is roughly 1.33. For many common forms of glass, it is around 1.5. This means that the effective propagation speed associated with the wave through the material is lower than the speed of light in vacuum. It is tempting to explain this by imagining a photon travelling through the glass, being absorbed by one atom, waiting for a moment, being emitted again, travelling to the next atom, and repeating the process. That story is common. But for ordinary transparent refraction, it is not a good description. If photons were repeatedly absorbed and then spontaneously re-emitted in this simple way, the light would generally lose much of the precise phase relationship and directional information required for ordinary transparent propagation. Spontaneous emission also occurs over characteristic timescales that do not match the smooth delay observed as light travels through a transparent medium. The better picture is a coherent interaction. The electromagnetic field influences the charged components of the material, and their response contributes back to the electromagnetic field. The incoming field and the response of the material combine. This changes the way the overall disturbance propagates. There are several different velocities that can be discussed here. The phase velocity describes how a particular phase of a wave moves through the material. The group velocity describes how the envelope of a wave packet propagates, and is often more closely connected with the movement of a light pulse and the transport of information under ordinary conditions. These velocities need not always be identical. In many transparent materials, both are affected by the interaction between the electromagnetic field and the matter. This is why saying that individual photons simply slow down like tiny cars entering heavy traffic can be misleading. The physics is not just about a little object reducing its speed. It is about the behaviour of a coupled system. The material also does not respond equally to every frequency of light. Its refractive index can vary with frequency. This phenomenon is called dispersion. Dispersion is why a prism can separate white light into different colours. Different frequency components propagate through the glass differently, and therefore refract by different amounts. Violet light and red light do not usually experience exactly the same refractive index. Their paths through the prism separate, producing the familiar spectrum. The microscopic reason ultimately comes from the frequency-dependent response of electrons and other excitations within the material. At an even deeper level, the distinction between light and matter can become less clear inside certain substances. When an electromagnetic field interacts strongly with excitations in a material, the combined system can sometimes be described using quasiparticles called polaritons. A polariton is not simply a free photon travelling unchanged through matter. It is a collective excitation containing both electromagnetic and material character. Depending on the material, the relevant matter excitation might involve electronic transitions, lattice vibrations, or other collective behaviour. This is a useful reminder that a photon in vacuum and an excitation propagating through matter are not always best described in exactly the same language. Inside a material, the electromagnetic field is continually coupled to the degrees of freedom of the substance. The excitation moving through the system can therefore behave as a mixture of light and matter. None of this means that photons contain hidden machinery that switches on when they enter glass. The photon does not suddenly reveal gears, brakes, or some microscopic device that makes it move more slowly. The apparent reduction in propagation speed comes from interaction. In vacuum, the electromagnetic field propagates without the response of a surrounding material. Inside glass, water, or another transparent medium, the field is coupled to charged matter, and that changes the collective behaviour. So when light passes through a window and arrives slightly later than it would have through the same distance of vacuum, the delay is not evidence that a photon stopped repeatedly along the way. It is evidence that the electromagnetic field and the material responded to one another continuously. The light we observe emerging from the other side still belongs to the same electromagnetic field, but while passing through the material, its behaviour was shaped by the quantum matter surrounding it. Even something as simple as a ray bending through a glass of water is therefore another example of the same deeper principle. Light is not an isolated little object moving through a passive world. It is part of a quantum field interacting with other quantum fields around it. Entanglement is one of the clearest examples of how quantum light refuses to behave like a collection of ordinary independent objects. Two photons can be prepared in a joint quantum state in which their properties are linked in ways that cannot always be reproduced by imagining that each photon simply carried a complete set of hidden classical instructions from the beginning. This is quantum entanglement. The crucial idea is that the full physical description belongs to the combined state. It is not always possible to describe each photon separately and then simply add the two descriptions together. For example, two photons can be prepared so that their polarizations are strongly correlated. If one photon is measured in a particular way, the result obtained for the other photon can show a matching pattern of correlation. That alone would not be mysterious. Classical objects can also be correlated. If one glove from a pair is sent to London and the other to Tokyo, discovering a left-handed glove in London immediately tells us what kind of glove is in Tokyo. But entangled photons go further than that simple example. The correlations predicted by quantum mechanics can be stronger than those allowed by broad classes of theories in which each photon carries predetermined local values for every possible measurement. John Stuart Bell found a way to test this difference. In the 1960s, Bell developed a mathematical result now known as Bell's theorem. From it came Bell inequalities. These inequalities place limits on the correlations that can be produced by a large family of local hidden variable theories. If experiments violate those limits under the appropriate conditions, then the observed correlations cannot be explained by simply assigning each particle its own independent set of predetermined local properties. This transformed a philosophical argument into an experimental question. John Francis Clauser and Stuart J. Friedman carried out one of the important early experimental tests using entangled photons in the early 1970s. Their results supported the quantum mechanical predictions and violated the relevant Bell inequality. Later, Alain Aspect and his collaborators performed more sophisticated photon experiments. Their work tested entanglement under improved conditions and addressed important weaknesses in earlier arrangements, including how measurement settings were chosen during the flight of the photons. Over the following decades, experiments became more precise and closed more of the remaining experimental loopholes. Anton Zeilinger and his collaborators pushed entangled photon research into increasingly elaborate territory. Entangled photons were used in demonstrations of quantum teleportation, where the quantum state of one system can be transferred to another distant system using entanglement together with ordinary classical communication. Zeilinger's work also contributed to long-distance quantum communication experiments and to increasingly controlled tests of quantum correlations. One widely used method for producing entangled photons is called spontaneous parametric down conversion. In this process, a photon enters a non-linear crystal. Under suitable conditions, the interaction can produce two lower energy photons, whose combined properties conserve the relevant energy and momentum of the original process. The resulting photon pair can be prepared with strong quantum correlations, including entanglement in polarisation, momentum, or other degrees of freedom. The phrase entangled photons can sometimes make the phenomenon sound as though the particles are secretly talking to one another. That is not the careful interpretation. Entanglement does not allow a controllable message to be transmitted faster than light. The measurement outcome obtained by one observer is not something that observer can freely choose and encode with useful information for the distant observer. To compare the correlations and reveal the entangled pattern, ordinary communication is still required, so no invisible signal needs to race between the photons carrying instructions after one measurement occurs. The striking feature is instead the structure of the joint quantum state. Quantum mechanics assigns amplitudes to the combined system. Those amplitudes determine the correlations between possible measurement outcomes. And the correlations can resist any explanation based on independent classical properties attached separately to each photon. This adds another layer to the question of what light actually is. Counting photons is not enough. Two states can contain the same number of photons while having completely different physical properties. The difference may lie in their phase relationships. It may lie in polarisation, it may lie in interference, and it may lie in entanglement between different parts of the electromagnetic field. So the quantum description of light is richer than a simple inventory of particles. Photons matter. But so does the quantum state in which those photons exist. That state can contain relationships that have no ordinary classical counterpart, and entangled light makes that point with remarkable clarity. What appears to be two separate photons can sometimes only be fully described as one shared quantum system. The photon is unusual in many ways, but one of its most important properties is also one of the simplest to state. As far as every experiment has been able to determine, The photon has no rest mass. That statement needs a little care. Experiments can place tighter and tighter upper limits on a possible photon mass, meaning they can show that if the photon does have any non-zero rest mass, it must be extraordinarily small. What experiments cannot do is measure an exact value of zero in quite the same way that they might measure a small positive mass. So the careful scientific statement is that no non-zero photon rest mass has ever been detected, and the evidence is overwhelmingly consistent with the photon being exactly massless. This is not just an isolated fact about light. It is deeply connected to the structure of electromagnetism itself. Modern particle physics describes electromagnetism as a gauge theory. Gauge symmetry is one of the central organizing principles of the Standard Model, and its roots can be traced partly to the work of Hermann Weyl in the early 20th century. The modern meaning of gauge symmetry developed considerably beyond Weyl's earliest ideas, but the basic principle became enormously important. In electromagnetism, different mathematical descriptions of the electromagnetic field can represent the same physical situation. The theory contains a built-in freedom in how certain field quantities are represented, while observable quantities remain unchanged. This gauge structure is closely connected to the photon. The photon is the gauge boson of electromagnetism. In the ordinary electromagnetic theory, introducing a simple mass term for the photon would alter this gauge symmetry and change the behaviour of the field. A massive photon would not merely be the same photon carrying a tiny extra amount of weight. Electromagnetism itself would behave differently. One particularly important change would appear over very large distances. With a massless photon, the electromagnetic interaction can extend indefinitely, weakening with distance but never acquiring a fixed maximum range. If the photon had a non-zero rest mass, even an extremely small one, electromagnetic fields would eventually fall away differently over sufficiently large distances. The familiar long-range form of electric and magnetic fields would be modified. Electromagnetic waves would also propagate differently. Their speed could depend subtly on frequency even in vacuum. And additional physical behaviour could appear that is absent in ordinary massless electromagnetism. Physicists can therefore search for a photon mass by looking for these kinds of deviations. So far, none has provided convincing evidence that the photon has non-zero rest mass. But masslessness does not mean that a photon carries nothing. A photon has energy. It has momentum. It can push on matter, it can be emitted and absorbed, and it can contribute to gravity. The confusion often comes from treating mass, energy and momentum as though they were interchangeable words. They are related, but they are not identical. Albert Einstein's special theory of relativity gives the general relationship between energy, momentum and rest mass. For a particle with zero rest mass, the relationship reduces to a particularly simple form. The energy of a photon equals its momentum multiplied by the speed of light. So a photon can have zero rest mass while still carrying both energy and momentum. This is why light can exert radiation pressure. When photons strike or reflect from matter, they can transfer momentum to it. The effect is usually tiny, but it is measurable. The same principle allows sunlight to push on a solar sail. A photon also contributes to gravity because, in general relativity, gravity is not sourced only by rest mass. Energy and momentum are part of the broader physical content that influences spacetime. Light can therefore be affected by gravity. And light itself carries energy that contributes to the gravitational description. There is another consequence of having no rest mass. A photon cannot be brought to rest in vacuum. There is no valid reference frame in which someone could travel alongside a photon and watch it sitting still. Every local inertial observer in vacuum measures light propagating at the speed of light. That behaviour is tied directly to the photon's massless nature and the structure of special relativity. So calling the photon massless should never be confused with calling it insubstantial or unreal. A photon can trigger a detector, it can knock an electron from matter, it can transfer energy across billions of light years, it can carry momentum from the surface of a star to a tiny grain of dust drifting through space. Masslessness is simply one of its fundamental physical properties, and rather than making the photon less real, that property is part of the reason light behaves so differently from the massive objects of everyday experience. The photon becomes even more interesting when we place it inside the larger framework used to describe the elementary particles of nature. That framework is the Standard Model of particle physics. The Standard Model describes the known elementary particles and 3 of the 4 fundamental interactions. It includes electromagnetism, the weak interaction, and the strong interaction. Gravity is not included in the Standard Model and is instead described separately, at least at present, by Albert Einstein's general theory of relativity. Within the Standard Model, particles are divided broadly into matter particles and force-carrying bosons. The photon belongs to the second group. It is the gauge boson associated with electromagnetism. That means the photon is the quantum excitation connected with the electromagnetic interaction. Electrons interact electromagnetically because they carry electric charge. Protons interact electromagnetically because their constituent quarks give the proton a net electric charge. Photons themselves carry no electric charge, but they are the elementary quanta of the electromagnetic field. For a long time, electromagnetism and the weak interaction appeared to be entirely separate forces. Electromagnetism acts over enormous distances. The weak interaction operates over extremely short ranges and is involved in processes such as certain forms of radioactive decay. But during the 20th century, physicists discovered that these 2 interactions could be described as different aspects of a deeper theoretical structure. This became known as electroweak theory. Sheldon Lee Glashow, Abdus Salam, and Steven Weinberg were central to its development. At sufficiently high energies, the distinction between electromagnetism and the weak interaction becomes less fundamental. Both arise from an underlying electroweak gauge theory. The familiar electromagnetic field is therefore not simply placed beside the weak interaction as an unrelated ingredient. The 2 emerge from a shared framework. Before electroweak symmetry breaking is taken into account, the theory contains several gauge fields. After the Higgs field settles into its non-zero vacuum state, combinations of those fields behave differently. One particular combination becomes the electromagnetic field. Its quantum excitation is the photon. Other combinations become the particles associated with the weak interaction. These include the positively charged weak boson, the negatively charged weak boson, and the neutral weak boson. Unlike the photon, the weak bosons are massive. The reason for this difference is tied to the Higgs field. The Higgs mechanism does not simply give mass to every elementary particle in the same way. The structure of electroweak symmetry breaking allows the weak bosons to acquire mass while leaving the photon massless. The electromagnetic gauge symmetry remains unbroken. As a result, the photon continues to behave as a massless gauge boson. This has enormous physical consequences. Because the photon is massless, electromagnetism can act over very long distances. The weak bosons, by contrast, are heavy, and the weak interaction therefore has an extremely short effective range. So even something as familiar as light is connected to a much deeper structure involving symmetry, quantum fields, and the Higgs field. And yet the photon itself still appears elementary. Experiments have found no evidence that photons are composed of smaller constituent particles. There is no confirmed photon core. There are no known subparticles hidden inside it. Within established particle physics, the photon is treated as fundamental. That does not mean physicists know with certainty that the Standard Model is the final theory nature will ever require. The Standard Model is extraordinarily successful, but it does not explain everything. It does not include a quantum theory of gravity. It does not identify the nature of dark matter. It does not fully explain the observed dominance of matter over antimatter. And it leaves other deep questions unanswered. Future physics may eventually reveal a more fundamental description beneath the fields and particles we currently call elementary. But possibility is not evidence. At present, there is no experimental reason to say that a photon is secretly made from smaller objects. So the most accurate picture remains the one provided by quantum field theory and the Standard Model. The photon is an elementary excitation of the electromagnetic field, and visible light is only one small part of what that field can produce. Radio waves are excitations of the same electromagnetic field. So are microwaves. So is infrared radiation. Ultraviolet radiation belongs to the same family. X-rays and gamma rays do as well. The differences lie mainly in frequency, wavelength, energy, and quantum state. There is no separate field for red light, another for radio waves, and another for gamma rays. They are all manifestations of one electromagnetic quantum field. That is the remarkable simplicity hidden beneath the enormous variety of light we observe. From a radio signal crossing a city to a gamma ray arriving from a violent event billions of light years away, the underlying quantum description points back to the same field. And the photon is the elementary quantum through which that field reveals itself. So what is light actually made of? According to modern quantum physics, light is described by the quantum electromagnetic field, and a photon is one quantum excitation of that field. A photon is not known to be a tiny object containing smaller pieces. Within the Standard Model of particle physics, it is treated as an elementary massless gauge boson with no experimentally established internal structure. It took centuries to reach that description. Isaac Newton imagined light as streams of corpuscles. Christian Huygens argued that light behaved as a wave. James Clerk Maxwell showed that light could be understood as an electromagnetic wave, while Max Carl Ernst Ludwig Planck and Albert Einstein revealed that electromagnetic energy is exchanged in discrete quantum amounts. Quantum field theory brought those ideas together in a deeper framework. Light can interfere and diffract like a wave, yet it can also transfer energy and momentum in individual photon events. Neither classical picture is complete on its own. A photon's energy, momentum, frequency, polarisation, spin, and helicity are not smaller ingredients hidden inside it. They are properties of the quantum excitation itself. Quantum electrodynamics then explains how the electromagnetic field interacts with charged quantum fields such as the electron field. Through those interactions, photons can be emitted, absorbed, scattered, created, and destroyed. That alone tells us something important. Light is not made from an eternal supply of indestructible microscopic grains. Photon number can change. And when enormous numbers of electromagnetic excitations occupy suitable quantum states, the familiar smooth behaviour of classical light can emerge. A laser beam, sunlight, and a single photon state can all belong to the same electromagnetic field while possessing very different quantum properties. Interference, coherent states, entanglement, vacuum fluctuations, and the quantum vacuum itself all reveal that the phrase light is made of photons is useful but incomplete. The deeper established description is the electromagnetic quantum field. Whether quantum fields themselves emerge from something even more fundamental remains an open question. Modern physics has no experimentally confirmed deeper layer beneath the photon. For now, every beam of sunlight, every distant star, every glowing screen, and every quiet bedside lamp can be understood as a visible expression of one of nature's fundamental quantum fields. Something wonderfully familiar, built from a reality far stranger than it appears.